Okay. So moving ahead with the machine learning library basics for our deep learning or our LP4 lab. So there are very conceptual building blocks that every deep learning technique is built directly on top of it. So we cannot understand a deep learning without these fundamentals. And so we are going through all these fundamentals. So where does the deep learning fits? I hope you all are very much aware about this diagram. The AI, ML, and deep learning. These are the nested categories, and they cannot be separated. We will not be able to separate it. So think like three concentric circles. The outermost circle is my artificial intelligence, the broadest field covering any system built to emulate the human decision making and perception. Inside to this artificial intelligence, we have the machine learning, a subset of AI, where the algorithms learn rules or the patterns statistically from the data rather than being explicitly programmed with the rules. And inside this machine learning, we have the deep learning, a subset of ML that uses the LED, a deep artificial neural networks, to learn representations of the data automatically without a human manually engineering the features. Now we'll see the vocabulary of this machine learning and deep learning. So before that, let us go and see what are the types of the deep learning model. So we have the supervised learning, machine learning. So we have the supervised learning that where we learn from the labeled data and use for the classification regression. Then we have the unsupervised learning. So finds the structured in unlabeled data. So used for clustering and dimensionality reduction. Then there is a reinforcement learning, so learns by trial and error, receiving the rewards, penalties for actions taken in the environment. And then lastly, we have the deep learning, which uses the many layered neural networks and often across all three learning types above and to learn the features automatically. Now look about what are these features, labels, and the vocabulary of the data, correct? So a feature, let us look at what we generally called a feature as. A feature is an individual measurable input variable. For example, a pixel value, a word frequency, or a house square footage, right? So that's my feature. Then there is a label. Now label or the label can also be called as a target and is the correct answer that a supervised model is trained to predict. For example, cat. For example, the house price. Then we have one more term. The next term is a feature vector. And a feature vector is all of a single sample's features combined into one array. So this is literally what gets fed into a model. So in images, the pixels themselves are the features. In the text, we have the word counts or the embeddings serve as the feature. Now moving ahead to the next concept. The next concept is a train, validation, and test split. So we never train and evaluate a model on the exact same data. That would give a falsely optimistic picture of how well it performs. What we have to do is a data set is typically split into three parts. Roughly a 70% training set used to actually fit the model's weight. Roughly 15% validation set used to tune the hyperparameters and monitor the progress during training and without touching the final data set, and roughly 15% test set used only once at very end to get an unbiased estimate of how the model will perform on the completely unseen data. So this is what how we divide our data set into three parts. Again, I will repeat: a training set is the roughly 70% and used to fit the model's weight. Then we have the 15% validation set and used to tune the hyperparameters and monitor the progress during the training without touching the final test set. And then we have the 15% test data set, which is the only used at the end to get the unbiased estimate of how the model perform on completely unseen data. Right. So let us see how does it work. So it is a general model training cycle we will like to see. So in every machine learning or a deep learning project, no matter how simple or complex, it follows the same first step. cycle, first five cycle. So first we have to collect the data, that is gathering the features and the labels. Then pre-process, clean it, normalize it, and split it. Then there is a train model, so fit it on the training data. Evaluate, checks its performance on the validation or the test data, and then improve, tune the model, and retrain if the results are not good enough. So these are the five steps which, or you can say this is the training cycle which always happen in every machine learning and deep learning project. So exact cycle applies whether you are training a simple linear regression model or a deep neural network model. Whatever you do, the same cycle has to be followed. Then there are two more important concepts which comes always in the machine learning. So they are overfitting and underfitting. Now, so let's see what does this exactly mean. These two are the classic failure model modes of any trained model, and they are opposite of each other. So this basically gives us the failure of the modes. Correct. So underfitting happens when the model is too simple for the data. It performs poorly on both the training set and the test set. So to fix this underfitting, we usually use the bigger models and more features, or we train for the longer duration. So that's what the my underfitting is. Now look at the overfitting. Overfitting happens when the model memorizes the training data too closely. It gets great accuracy on the training data, but poor accuracy on the test data because it has not actually learned generalizable patterns, just memorized specifics. So that's what is my overfitting is. So over here, it just memorized too closely. So it gets a great accuracy, of course, but training data on the training data, but the pure accuracy on the test data. So what we have to do in the case of overfitting, so to fix is more data regularization or dropouts or early stopping. These are the way for handling the overfitting in the machine learning algorithms. So, now we'll see. So these are the basic terminologies which used in the machine learning. We'll see a few common evaluation metrics. So let's see the evaluation metrics. So we have the accuracy. Then we have the accuracy. Just a we have the accuracy as the training matrix, evaluation matrix. So accuracy is the percentage of a prediction that were correct overall. Then we have the precision, like everything the model predicts as a positive. So how many actually were positive? That's what my precision is. Then the recall asks for the reverse. Then like all of all the actual positive, how many did the model correctly identify? Okay, that's my recall. Then F1 score is the harmonic mean of the precision and recall, balancing both into the single number. Useful when we care about both false positive and false negative. Then we have the confusion matrix. So this confusion matrix is then this confusion matrix is a table showing the correct versus the incorrect predictions broken down per class and giving us a detailed picture beyond the single accuracy number. Now, as usual, we'll go for the few questions, quick questions. So, what is the difference between supervised and unsupervised learning? So, supervised learning on the label data and unsupervised learning finds the patterns in the data that has no labels. The second question is why keep a separate validation set instead of just using the test set? So, validation set lets us tune the model and make the decisions during the development, keeping the test set untouched for one final and unbiased evaluation. Then the third question is the model gets 99% training accuracy, but 60% test accuracy. What's likely happening? So this is a classic sign of overfitting. The model has memorized the training data rather than learning the patterns that generalize it. Now moving ahead to the data sets part, the next section. So here, like we will be looking into like where the data comes from. So every machine learning and deep learning model needs the data to learn from. And this particular section covers what that data look like and how to prepare it properly, right? So let's see first what is data set. A data set is a simple and organized collection of a data samples used to train and evaluate a model. We have the tabular data sets, which are organized as a rows and columns. So, like a spreadsheet, we have the image data sets, which is the collection of image files, usually paired with the label pair per image. And then we have the text data sets, which is the collection of the documents, sentences, tokens, often paired with either a classification label or the next word for the predict. Let's see what is the structured and unstructured data set. Okay, unstructured data. So this distinction determines which tool and technique is appropriate for the given data set. So when we have the structured data, it is organized in rows and columns, just like a spreadsheet. For example, include the sales record, sensor readings, and the survey data. It's typically handled well with the pandas, scikit-learn, and then we have the unstructured data, so which has no fixed rows and columns format. Examples include the images, audio, free-form text, and video. Because there are no natural tabular structure, unstructured data is typically handled with deep learning using the architectures like the CNNs, RNNs, and the transformer. Right? Let us look at the benchmark data set, which we all will be using in our LP4 lab. So we have a few data sets showing us as the standard and again as a benchmark. So one is MNIST, which contains 70,000 grayscale images of handwritten digits 0 to 9, and it's often called the hello world of the image classification because it's a small, simple, and quick to train on. Then we have the CFAR 10 contains the 60,000 small color images across 10 classes like airplane, dog, truck, set up in a difficulty from the MNIST. Then we have IMDb reviews, which contains 50,000 movie reviews labeled positive or the negative, the standard database for the text classification and sentiment analysis. And lastly, even there are the IRIS, Boston Housing datasets, which are small, classic, tabular datasets used to teach the classification and regression fundamentals. So out of this, I think you have used few datasets in your third year also. So these are the simple datasets which we will be using. Again, we'll see the data pre-processing pipeline. Now, why we require the data pre-processing? Because the data is not clean. It contains the noise. So before modeling any of the data, before training the data, it goes through these pre-processing steps. So we have the first step as a cleaning the data set. So handles missing or the duplicate values. Then we encode, that is convert the categorical values like cat, dog into the numbers the model can actually process. Then we have the normalization or normalize, which scale all the values into a common range. So no single feature dominates just because of its scale. This is a third step. And then the fourth step is a split. So divide the data into the train, validation, and test sets. So getting this pipeline right matters just as much as the model itself. So, as we all know, the old saying that is garbage in and garbage out. So, it same applies to our world of deep learning and machine learning. So, first you have to clean the data, make it pure, and then only you will be going to get the good output. That's what the data pre-processing pipeline says. And then there are a few question answers, a very simple one. And now we will move to this epoch, batch, and iteration. These are also very important concepts if we look into. And we always say while the coding, we this much of batch, this many iterations, some epoch. But what does it actually say? Right? This is also the vocabulary of the deep learning and machine learning. And we all must know this vocabulary. So look at the distinction or what does this epoch, batch, and iteration mean? This is what we will be looking into. So now this pictures the full training data set. So instead of feeding the entire data set into model at once, we split into smaller chunks, which is called as a batches. Again, I will repeat. Instead of feeding a complete data set, to the model, we split the data set into smaller chunks and which are called as a batches. So we have the batch 1, batch 2, batch 3, and so on. So each time one batch passes through the model and weights gets updated, that that's called one iteration. Please remember. So one batch passing through the model and getting its weights updated, that's called as a iteration. So once all the batches have been processed, सारे batches, ये complete data set है, उसको batches में divide किया है, and once you process all these batches, what does it mean? It means that the model has seen the entire data set once, and this is called as one epoch. So training then repeats this. Correct. I hope you understood. Epoch किसे कहते हैं? Your model is looking at all the batches. That is entire data set once. That is my one epoch. Correct. So once all batches have been processed, meaning the model has seen the entire data set once, that's called as one epoch. Training then repeats this whole process for a chosen number of epochs. Generally, at the start, we decide the epoch and we repeat the process. So going through the full data set multiple times so that model keep on improving, keep on learning. So to summarize, batch size is the number of samples processed before one weight update, and the epoch is one complete pass through the entire training data set. Okay, I hope this is clear with all of you, and we'll move ahead. So the key terms are there. These are the batch size, is the number of samples processed before the model weights are updated once. Iteration is one single update state that is processing exactly one batch. Epoch is one complete pass through the entire training data set, meaning all the batches have been processed once. And then we have the term as a learning rate, and it is how the large step the optimizer takes when the updating the weights during each iteration. Right? So these are the simple terms which we will be using consecutively in our sessions. Next, we have why learning rate matters. The learning rate controls how big a step the model takes when adjusting its weights, and getting it wrong causes a real problem. So if we have the learning rate too high, the training can overshoot the optimal weights and never converge. Please remember. What did I say? If we have learning rate as very high, the training can overshoot the optimal weights and never converge. The loss bounces around or even explodes upward instead of decreasing. This is how the uh, very high learning rate is going to impact. And if it's too low, the training converges extremely slowly, wasting the time and computing the resources. A well-chosen learning rate steadily reduces the loss across the epochs toward a good solution. Right? So a starting point in many deep learning workflows begin with the common default 0.01, which is typically for the Adam optimizer, and adjustment made on the basis of this to actually receive to the our own goal. We'll see a few question answers quickly. So if data set has 1,000 samples and the batch size is 100, how many iteration make one epoch? So 10 iterations, of course, because 1,000 samples, a batch size 100, so 10 batches per epoch. Does training for the more epochs always improve the model? It's not necessary. Beyond a point, more epochs can lead to overfitting. What I say, the overfitting में क्या होता है? It learns, it memorizes the data. So where the training accuracy keep rising, but validation tech performance gets worse. Like then why not just use the entire data set as one giant batch? Because large batches demand more memory and can generalize slightly worse. Smaller batches introduces helpful noise and it let weights update more frequently. Now going for the last part. The last part is writing our first code, right? And so how do we write? This is all of you are very much aware. So what we are doing is np.array It converts a plain Python list into the first NumPy array. You can see from the example. So once you have that array, attributes like the dot mean, dot shape describes the data instantly. Dot mean here is returns 3.0 and dot shape returns 5, meaning it's at one dimensional array with the 5 elements. The real power of NumPy shows in the last line that normalize equal to data divided by data.max. So what does it do? It divides every single value into array by maximum value all at once. So no manual loop is required. So this is what called as a vectorized operations mean. So as I said, the NumPy support the vectorized operations, and this is the example of the vectorized operation. Then next we have loading and exploring a dataset, that is pandas. So here we use pd.read.csv and student.csv. It loads the tabular data straight into the pandas data frame. And once loaded, a df.head shows you the first 5 rows. So you can eyeball what the data looks like. And df.describes you the summary statistics, mean, standard deviation, mean, max, and so on. Then for every numeric column, df.isNull.sum counts how many missing values exist in each column. So these three commands should be the very first thing you run on any of the new data set, because catching missing values early avoids the problem later during the model training. Moving ahead to the matplotlib. So here we have the plot, epochs and laws, draws a line chart. So here plotting loss values against the epoch numbers, which is exactly how we will visualize a training curve later in this our lab, LP4 lab. So plot.x label, plot.y label, plot plt.title. These are going to add the labels and the title to make the plot self-explanatory. Always label your axis, and since that habit carries into every experiment, we will run. Finally, plt.show render the figure. In a script, we need this line exclusively. But if you are using a notebook, then the plot often appears automatically after the tail runs. Now look at the scikit-learn. What does the scikit-learn do? So the train test split automatically divides our data XY into training and the test portion. Here 20% is held out for the training via test size equal to 0.2. What we have to notice the pattern and the create the model. The model is created with the logistic regression, and fit is an training data with the model.fit, xtrain, ytrain, and evaluation it with the model score, that is x test and the y test. So this creates the fit score pattern and is used by virtually every model in this scikit-learn, regardless of which algorithm we choose. And importantly, this exactly pattern carries out almost unchanged into the deep learning code also. Then we will look at the Keras, the next example, a neural network which with the Keras. So here is the preview of what full deep learning code will look like. So Keras.sequential, you can see over here. This Keras.sequential builds a model layer by layer. One dense layer of a 64 units with a ReLU activation, followed by a dense output layer of a 10 units with the softmax activation, typical for the 10 class classification problem. Then we have the model.compile configures how training will happen, which optimizer to use, and which loss function to minimize, and which metric to track. So finally, we have the model.fit, xtrain, ytrain, epoch 5, and batch size 32. So actually trains the model and notices epoch equal to 5 and batch size equal to 32. It maps directly onto the exact concept we just covered into the epoch and the batch section. So this is the same fit compile pattern we see in the scikit-learn, just applied to a neural network, and then our pattern is ready. So lastly, the last part is a few question answers. So what is the common pattern shared by scikit-learn and Keras model code? So both follow, create, define the model, fit it on the training data, evaluate score, or the predict on the new data. The next part is why check if df is null.sum before training any model. So missing values can break the training or silently bias results. So identifying them early lets us clean or impute the data properly. The next question is, in the Keras example, what do the epoch 5 batch size 32 controls? So epoch 5 means the model passes over the entire training set 5 times batch size equal to 32 and means weights update after every 32 samples. So here now we are ready for our LP4 lab. So what we have seen the Python, how to write the simple code, how to run the code, what are the different libraries, basic building blocks, loops, control structures, then ML concepts, training, test, validation data set, overfitting, underfitting, evaluation metrics. Then few training vocabularies like epoch, batch, iteration, learning rate. So these are all the basics of the basics which we should know before going for the deep learning lab. So thank you all.